Hi, this is Alex from devstories.eu, Mastering DeepChem, Episode 1 of 15. You want to apply machine learning to a scientific problem, so you reach for standard tools. But those standard tools treat molecules and proteins like flat data arrays, completely ignoring the underlying physics. The tool that bridges this gap is the DeepChem project. People often assume DeepChem is a standalone tensor engine, something you use instead of PyTorch, TensorFlow, or JAX. That is incorrect. DeepChem is a domain-specific toolset built directly on top of those generic frameworks. It acts as a translator. It takes care of the complex engineering required to turn messy physical data into a format that a standard neural network can process. The project exists to democratize deep learning for science. When it started, the focus was strictly on chemistry. The initial goal was to make drug discovery accessible, giving researchers the tools to predict chemical properties without needing a massive proprietary laboratory. But as the field grew, so did the framework. Today, DeepChem has quietly evolved into a central hub for almost any scientific deep learning application. To understand this scope, consider the difference in domains it handles. On Monday, you might use DeepChem to predict the aqueous solubility of a new drug-like molecule. This requires a model that understands molecular bonds and quantum states. By Thursday, you might use the same framework to analyze a microscopy image to count individual cells. Those are vastly different physical problems. DeepChem abstracts away the underlying boilerplate for both, providing specialized tools for molecular machine learning, bioinformatics, and even materials science. Here is the key insight. The hardest part of scientific machine learning is data representation. A standard deep learning model has no concept of atomic structure or biological sequences. DeepChem solves this by providing highly tuned featurizers. A featurizer takes a raw scientific object, like a chemical compound written in standard text notation, and mathematically translates it into a graph or a vector. After featurization, the information goes into specialized DeepChem dataset objects. These objects are designed to efficiently manage large collections of scientific data on disk. This prevents memory crashes when you process millions of complex compounds. DeepChem also addresses how scientific models are evaluated. In standard machine learning, you typically split your training and testing data randomly. But in chemistry, random splitting causes models to memorize the training data rather than learning the actual physics. To fix this, DeepChem provides specialized splitters. For example, a scaffold splitter separates molecules based on their core two-dimensional structure. This ensures your testing data represents entirely new chemical families, forcing the model to prove it actually generalizes to unseen compounds. Once your data is prepared and split, DeepChem provides an entire suite of pre-built models tailored for these datasets. You pass your scientific objects to the featurizer, DeepChem converts them, handles the splits, feeds them into the underlying PyTorch or TensorFlow layer, and outputs a prediction. The real power of DeepChem is that it encodes domain knowledge directly into your data pipeline, allowing you to focus purely on the scientific discovery, rather than the structural plumbing of machine learning. If you want to help keep the show going, you can search for DevStories EU on Patreon. That's all for this one. Thanks for listening, and keep building.